Welcome back. Now we will automate this calculator using Redstone and logic gates. For now we will support only one operation, which is adding. We will do subtraction, division and multiplication later. Before automating it, we need to know how addition works. This is base 10, decimal. So if we add 9 to 99, what we are actually doing? We are adding 9 to 9, we put 8, then we carry over 1, then we add this 1 to 9, which is 10, we put 0 here, and carry over 1, and we set it here. So by putting 8, 0, I mean actually sum. So sum of 9 and 9 is 8, then sum of 1 and 9 is 0, but it has a separate column called carry. This operation does have a carry, this as well. The next operation is actually adding 1 to 0. It does not have a carry, so it's 1, 0, 8, which is 108. I'm back here at the base 10 showcase to explain why I picked number 9 and 99 to showcase addition, because when you get a number bigger than 9, like let's say 10, you need to move to the next position, and this is called carry over. So when we added 9 to 9, it does not matter what the output is here, but the thing is that we carried over to the next digit, and this operation had an output of 1 carryover and sum. In that case, sum was 8, and the sum is saved to the current digit, but the carryover is carried over to the next digit. And as you can see, when you carry over, since it's addition, it will be always 1. For example, if we add 3 and 7, it will be 0 here as sum, but the carryover will be 1. If we add 9 with 9, which is maximum, we will have 1 anyways. That's the case for addition. Here I have two numbers, 9 and 11. Let's add them together in binary. So let's first represent them in binary. To represent number 9, we put number 8 and set it as 1. Then 0, 0, which means 0 basically. This is 1, and we set it as 1. So 1 plus 8 is 9. That's the binary representation of number 9. Now same for 11. 8 plus 2 plus 1 is 11. Now let's add them together. In base 10, the biggest digit is 9. In base 2, the biggest digit is 1. So adding 1 with 1 is similarly to adding 9 to 9. As you can see, we set the sum here, then we carry over. Same here. Their sum is 0, but we carry over. When we carry over, we are actually adding 3 numbers. The carry, this number, and this number. So 1 plus 0 is 1, then 1 plus 1. Their sum is 0, but we carry over. And we repeat the same for the next digits. 1 plus 0, it's 1 because its carry over is on, so on means 1. 1 plus 0 is 1, and 1 plus 0 is 1. Their sum is 1, we don't carry over anything. Now, if we do the same thing for the next position, 1 plus 1, their sum is 0, and we carry over, since this is imaginary next digit, it's 0 here, and we set on 1 here. Now we have this output, 1, 0, 1, 0, 0. Let's check what number is that in decimal. Here it is. It's 20. We added 11 to 9, and that's correct. It should be 20. When I was explaining base 2 in the previous episode, we start with number 1, then we multiply by its base and continue, and we get bigger numbers. If you were confused why this is 1, this is 2, this is 4, and that is 8, that's the reason why. Same here. We have 1, 2, 4, 8, and 16. After we added those two numbers together, we got this output. So 16 plus 4 is 20, and makes total sense, right? You will notice the fact that when 1 and 1 meets each other, their sum is 0 and the carryover is 1, right? So here we have it. This is the first number, this is second. Their carry is 1, their sum is 0. When 0 meets 0, their carry and sum is 0. When 1 meets 0 or 0 meets 1, their carry is 0 and their sum is 1. Does this and this look familiar to you? Have you ever seen before 0, 0, 0, 1? This is AND logic gate. So carry can be represented by using an AND logic gate. When both are turned on, this is on. What about sum? Which logic gate can represent it? Let's go here and we will analyze it. So we need 0, 1, 1, 0. Is it OR? No. Is it not? Of course not. Is it AND? No. Is it XOR? It's 0, 1, 1, 0. It's exactly what we need. So to represent sum, we use XOR logic gate. To represent carryover, we use AND logic gate. This truth table is applied when first number is 1 bit long, second number is 1 bit long. But our numbers, each of them is 4 bits. So we need a way to add them by having 4 bits, right? Let's automate first this table. Memorize these colors. X is orange, Y is purple, C, carry, is AND logic gate and is yellow. Here we are back at the AND logic gate. I will use this compact version of it. And here it is. AND logic gate, first input, second input. Also we need to perform sum, right? By using XOR logic gate. Again, which flavor we will use? I picked this one because it's quite compact and it's simple to understand. Here we have it as well. Input on the left, input on the right. We have repeaters here because we need to check if it's asymmetric or not. Now let's test this. Carry is on only when both are on. We will test this first, then the cases when they are different, basically meaning 0, 1 or 1, 0. And when they are 0, 0, both should be 0. Carry is 1 when both are 1, testing that. Indeed, it's 1 and sum is 0. Then 0, 1 is 1, 1, 0 is 1, and 0, 0 is 0. How do we read outputs from the addition point of view? 1 plus 1 should be 2, right? So this is 1, this is 0. 1, 0 in binary is 2. Here I am back to manual calculator and 1 plus 1 is 2. This is AND logic gate, this is XOR logic gate. Their sum is 1 when they are different. 1, 0, 0, 1. When all of them are turned off, everything is 0. That's why we have this middle line to showcase that the output is 2 bit long, but the inputs are 1 bit long. X is 1 bit long, Y is 1 bit long, but the output can be 2 bits long. 1, 0 is 2 in binary. And this, my friends, is called half adder. Here we have it. If you want to make one by yourself in real life, not in Minecraft, here is the schematic, truth table, logic gates, and the real implementation using a breadboard, some resistors, cable, transistors, and that's it. Now we have this implemented, but we want to add bigger numbers, right? Not just 1 bit long. We need 4. Let's keep adding bits to this table. In order to add bigger numbers, we need to analyze what happened here. When we added these two guys, we had a carry out. But what is this carry for this position? It's not a carry out anymore, it's a carry in. Our digital circuit should support not only carry out, but carry in as well. Let's implement that. Before we had half adder. Half adder does not support carry in. To support carry in, we need full adder. This is the schematic for full adder in real life. I will show you now how to do that in Minecraft. One way to achieve full adder in Minecraft is to combine two half adders, like here. Here we have carry in. It's combined with the sum from the previous operation. And we have again a carry out from here, a carry out from here, and we have sum. Here is the top view of it. Carry in goes here as right input for the next half adder. First half adder has an output of sum here and goes as left input here. Now the question is left what we are doing with the carry out from the first operation and carry out from the second operation. We just need an OR logic gate. As a result, we have carry in, carry out, and sum. Now let's add two numbers, 9 and 11 again, but we will separate the operations one by one because we don't have a circuit to execute the entire calculation yet. We will do that, don't worry. Let's start with this first. Since This is our first position. There's no carry in. Imagine it's 0 by default. Then we have a carry out of 1, because 1 plus 1, their sum is 0, but the carry out is 1. If you remember this table, carry out is 1 when both inputs are 1. Both of the inputs is 1, so left bit is 1, right bit is 1. Their sum is 0, carry out is 1, carry in is 0. Let's try that right now. Left bit is 1, right bit is 1, carry in is 0. As a result, their sum is 0, but carry out is 1. Carry out is 1, sum is 0. Isn't that correct? Imagine we are here, and we have a carry in, the left bit is 0, right bit is 1. Carry in is 1, left bit is 0, right bit is 1. Here is our sum and carry. Carry is 1, sum is 0. And that's true. Carry out is 1, but the sum is 0. Now next position, we have carry in, which is 1. Bits are set to 0. Their sum is 1 because of the carry in. The carry out is 0. Bits are set to 0. Carry in is 1. Sum is 1. Carry out is 0. Is that correct? Carry out is 0, but the sum is 1. Now let's test our full adder on last bit, 4th bit. Carry in is 0. We have bits set to 1 and 1, so left bit is 1, right bit is 1. Their sum is 0, but carry out is set to 1. Both of the bits are set to 1. Carry in is 0. Carry out is 1. Sum is 0. Now let's check if it's correct. Left bit is set to 1, right bit to 1. Carry in is 0. Carry out should be 1. Sum should be 0. Are we done here? No. We have carry out. We need to do something with it. 9 plus 11 is not this number. This number is just 4. We need 16, right? So we move to the next position. The carry in is 1. Imaginary bits are 0. By default, imaginary bits are 0. Like here it was, carry out will be 0, but the sum will be 1. Here is our sum, here is our carry out. Again, carry in is 1, 0, 0, carry out is 0, sum is 1. Bits are set to 0, carry in is 1, sum is 1, carry out is 0. Will it make sense to move to the next position? No, because it will be 0 plus 0 plus 0, sum will be 0, carry out will be 0, and we can keep doing it forever. And just like that, we have a semi-automatic calculator that adds two numbers, but does not perform the entire calculation in one go. Now we will fix this issue. Before, we had one half adder to support carry in from the previous operation. We added another half adder. So our full adder now supports carry in, it has carry out, and makes total sense that this carry out can be a carry in for the next full adder, right? So here we have it. First full adder, second full adder, and this carry out now is a carry in for the second full adder. As a result, now we support two numbers, 2-bit each. Here it is, full adder that supports two numbers, 2-bit each. What name would be appropriate for such adder when we stacked two full adders? The conventional name for it is ripple carry adder because of this connection. The carry out of the first full adder is carry in of the second full adder, shown here. By stacking these full adders in this setup and matching left side of the second full adder with the left side of the first adder, it makes sense that since we were supporting before number from 0 to 1, here we support from 0 to 1, but the next one is the next power of 2. So if this was 2 to the power of 0, which is 1, so we can add 1 plus 1 here. The next full adder supports 2 plus 2, and as a result, we have 1 from here, 2 from here. We can support 3 plus 3. So the maximum output from this system is 6 by using X and Y inputs. Of course, if we add carry in as well, the result should be 7. Let's turn all of them together and see if that is the case. Yes, we have 1, 2, and 4. Added together is 7. And we have all of them turned on. Now ignore this for now. This is a special carry in bit. Let's add these two numbers. Here we have 1 and 2. We can add 3 plus 3, right? Let's do 3 plus 3. 3 plus 3. It's 6. This is 1, this is 2, this is 4. 4 plus 2 is 6. Think of another number. Let's add, I don't know, 2 plus 1. 1 plus 2 is 3. Simple, right? We tried to turn all of them on. We tried number 6, number 3. Let's do number 1 here. Now 1 plus 1 is 2. Then let's do 4. 1 plus 3, it's 4. Then let's do 5. Here 2, here 3. 2 plus 3 should be 5. 4 plus 1 is 5, so it's correct. And that's kind of it. This is 2-bit RCA adder. To achieve 4-bit RCA, we just need to copy this and paste there. And again, the carry out of both of these will be the carry in of the same thing, but copied. So we will have 4-bit RCA. What about stacking it in width, not in length? Here is the modified full adder. We have the carry in on the right side, carry out on the left side. Then we can stack 4 of them and it will become 4-bit RCA. Now we support 4-bit numbers as input, and we can finally add 9 to 11. In this manual version of an adder, we supported only 2 bits. The first number was 2 bits and second number was 2 bits. Now, not only we automated this already, now we support 4 bits, and our 4-bit RCA will look like this. It will have a carry out here, and this 4 will be the sum, and we can have 2 numbers, 4-bit long each. We had that previous example adding 9 to 11. Let's add this right now. When we can't fit a number into one binary digit, we just expand by multiplying by its base. So basically 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, 4 multiplied by 2 is 8. Same principle applies here for these full adders. This is a full adder supporting 1 plus 1, this is 2 plus 2, 4 plus 4, 8 plus 8. Our first number is number 9, so this is 8 plus 1, again 8 plus 1. We have 9. These lamps are off, and our second number, marked in purple, is 11. 8 plus 2 and 1. 1 plus 2 is 3, plus 8 is 11. Let's read the output as well. Here we have 1, 2, 4. 4 plus, this is 8, and this is 16. So 4 plus 16 is 20. Let's verify it with our example. We had 1, 0, 0, 1. This is 1. This is 0, 0, 1. Then we have 1, 0, 1, 1, 1, 0, 1, 1. And the result was 1, 0, 1, 0, 0, 1, 0, 1, 0, 0. Why do we count this as sum? It's actually this case, when we had a carry out here. Do you remember what we did before? We moved to the next position. We treat it like carry in, not carry out anymore. So for this position, it becomes carry in. We add 1 to 0, which is 1, then 1 to 0, which is 1. And that was our sum. It was 1. We had 2 numbers, 4 bits each. But our output is not 4 bits. It's 5 bits. And we used this property here. This is our 4 bits, 1, 2, 3, 4. And by having this carry out set to true here, we basically are asking for a higher number than 8. And the next number after 8 is 16. That's why we can treat this carry out when it's turned on as 16. Let's add one last number. You can try it by yourself, download this map, and add as many numbers as you want. But keep in mind the maximum number that we support is 15 here. So we support 15 plus 15 plus a carry in. I will do 5 plus 7. Let's set x to 5. So I have for now just 4. Let me add 1. Now we have x set to 5. Let's set y to 7. 4 plus 2 plus 1 is 7. So here I have x set to 5. 1 plus 4 is 5 on orange side, and on purple side, which is y number, it's 4 plus 2 plus 1, which is 7. So 5 plus 7 is 12, because 8 plus 4 is 12. And if we read it in binary, we added 0, 1, 0, 1, 0, 1, 1, 1. And the output is 0, 1, 1, 0, 0. If we ignore that, it's 1, 1, 0, 0. 1, 1, 0, 0 is 12 in decimal system. And that's it for this episode. It's already quite long. Remember, our task was to automate this manual adder, and we finally did it. We finally added 9 plus 11, and we got our 20. We tried another number just to showcase it's working. The next episode will have a new link to this map that is updated. This is the end of this map for now. I will need to construct the next episodes there. See you next time.